First of all, I want to thank the organizers for this opportunity. This is actually my first international talk, so I'm a little bit nervous. And also, I want to thank you all for being here. What I want to tell you today is my work with Professor Marcelo Viana regarding the continuity of Lyapunov exponents, specifically in the case that you have a measure with non-compact support. So thankfully, in the morning talks, a lot of the speakers talk about Lyapunov exponents, but let me put you in my context, okay? So we are considering here the shift map. You have the sequences, the one-sided sequences over the SL2 matrices. And we consider this function, what I call the linear cocycle A, which actually takes a sequence and gives you the first coordinate, okay? We actually define the dynamically the iterates of this map A to be the product of all the first K matrices. That's why we call this kind of linear cocycle the random product of matrices. Actually, I forgot to put it here. We are going to consider a probability measure P on the space of SL2 matrices. And the measure over M will be the Bernoulli measure given by this product, okay? So in that case, Furstenberg-Kersten proved that if we have this integrability condition, these limits exist mu almost every point, okay? Actually, these functions are invariant by the shift map. So if you consider an ergodic measure mi, this actually is going to be a constant for mu almost every point. And by the multiplicative ergodic theorem, you have these two identities. The upper Lyapunov exponent of lambda plus is equal to this infimum, and the lower Lyapunov exponent, which is lambda minus, is equal to this sub, okay? Actually, we have a relationship of these two numbers, and it's that lambda plus lambda minus is equal to 0, okay? The P is a measure in SL2, but mi is a measure on the shift map. So actually, since the cocycle is locally constant, you can change mi by P here, because the cocycle takes the whole sequence but gives you only a matrix A0, the first coordinate. So if you see here, these numbers actually are function of the measure. So what we want to do is to study how they behave when you perturb the measure. First of all, we need to define what topology we're going to work on. The usual topology that we work with is the weak start topology. That is, you say the mi n converges to mi if this limit goes to 0 for every bounded and continuous function. Or, as in the first talk they said, you can change continuous function but Lipschitz with constant 1, okay? But the bounded condition is very important. So if we go back in here, consider only the integrals, okay? If our measure mi has compact support, then the cocycle A is bounded. So all the function of the logarithm will be a continuous and bounded function. So this integral will converge in the weak start topology. So our first result is that you have the lambda plus is upper semi-continuous and lambda minus is lower semi-continuous. So actually, if you have 0 Lyapunov exponent, in that case, these two are going to coincide. You will have from one side upper semi-continuity, from the other side lower semi-continuity, right? So 0 Lyapunov exponent, you have a continuity point. That's in the compact setting. With lower semi-continuity, and Bocker-Viana extend the result for to guarantee actually continuity of measures. Here, he restricts themselves to the weak start topology for the measures, and also you need a Hausdorff topology to the support of the measures, okay? So you need the measures to be continuous in the weak start topology, and the compact support has to be in the Hausdorff topology, okay? So what I wanted to do is generalize this to the non-compact support, okay? So what happened is that we actually don't even have semi-continuity in this case. Why? Remember that when I defined the weak star topology, I said that you need to be bounded, the functions, right? When your support is not compact, the co-cycle is no longer bounded. So here we construct an example. We numerize a sequence of numerable matrices. All of them are hyperbolic, very, very contracting and expanding in one direction. The impar are expanding the horizontal and contracting in the vertical. The odd ones are contracting in the horizontal and expanding in the horizontal, contracting in the vertical, and the other ones do exactly the opposite, okay? So if you construct these weights here, since you see the weights for P2K and P2K minus 1 are actually the same, right? So when we are expanding in one direction, then in the same way appear the other one, and that's the other thing around, right? So we actually have 0 Lyapunov exponents. The behaviors kind of cancel each other. If you just change one of the ways to be different, you no longer have 0 Lyapunov exponent. 0 Lyapunov exponent. You actually has this equality here. So you no longer have semi-continuity in the non-compact case. So the weak star topology is not good enough. So we need something stronger. That's why we use the Wasserstein space. The Wasserstein space, you consider the measures, which are probability measures that has a finite first moment, okay? Which is this integral here. This definition does not depend on the point that you fix, the x0. And in this case, we have some good properties for the Lyapunov exponents. First of all, is that the Lyapunov exponents will always exist. Why? Remember that the Furstenberg-Kirsten result says that the Lyapunov exponents exist if you have the integrability condition, right? In this case, since we are in matrices with SL2, their norm are always bigger than 1 or equal than 1. So this function is actually Lipschitz. You have that last inequality between the logarithm and the distance. And since we are in the Wasserstein space, the first moment is always finite, okay? So we always have the integrability condition, so the Lyapunov exponents will always exist in this case. So what's the topology that we use in the Wasserstein space? In this case, we use the weak star topology, and also we need the convergence of the first moments, okay? So it's a little bit more stronger than the weak star topology. And also, you know that it can be matriceable. You can consider this Wasserstein distance that was mentioned in the first talk this afternoon, where you consider this sub over all the Lipschitz functions with constant 1. When we are considering a compact space, this actually coincides with the definition of weak star topology. But in general, it doesn't, okay? So something that's good about the Wasserstein topology is that you have a lot of equivalences. For example, we have these properties here. We said that a sequence of measures converge to me if, for example, they converge in the weak star topology, and you have that this limit here goes to 0. So you can have like a very big ball, and outside this ball, all the integrals of every μk are as small as you want, okay? So you can control what's going on outside a compact set. Or you have this other equivalence that is similar to the one of the weak star topology. We have a function that has this bounded here with the distance, and in this case, these two integrals converge. So what does this help us to do? We actually prove that using these properties, we regain again the semi-continuity. How do we do this? We consider stationary measures. When you're working with Bernoulli shift, which is our case, you can define these measures of the new measures. And Furstenberg actually proved this equality here, that the upper Lyapunov exponent coincides with the maximum of this over these stationary measures. So in this case, for example, if you have a sequence μn converging to me in the Wasserstein topology, okay? For each μn, you can consider a station, well, because actually we can consider, remember that μn is equal to some measure Pn. So we can consider Pn converging to the Wasserstein distance measure P. And we can consider here a stationary measure for Pn, that one that attained that maximum, okay? So we can guarantee that lambda plus of Pn is this integral, okay? So actually this set is compact on the weak star topology. So passing by a subsequence, you can guarantee that it converges to another measure, nu, that is a stationary measure for P. But you cannot guarantee that this stationary measure is the one that attained the maximum, okay? So we can, if we can prove that this integral converges to this, we already have our semi-continuity, because this one is going to be less equal than the Lyapunov exponent, okay? So remember, we cannot apply the definition of the weak star topology here because this function here is no longer bounded, okay? But what do? We take a special compact set and we separate both integrals, inside the compact set and outside. Outside, we use the first condition. So we take the compact set, so the integral, these integrals outside the compact set are as small as I want. And inside the compact set, I use the second condition, okay? I have to be careful because when I restrict myself to the compact case, I actually multiply by the indicator function, but I can approximate by bounded functions. So that in that case will be continuous. And that's why how we prove the semi-continuity in this case. So, okay, we already achieved our semi-continuity. Next step is to prove the continuity, right? So our surprise is not possible to have continuity in the non-compact set, non-compact setting. Why? Because you have this problem here. Consider, for example, these hyperbolic matrices here and the rotation, okay? In the first measure K that we define, we forget about the rotation and only consider the hyperbolic matrices, okay? Again, in that case, you can compute directly the Lyapunov exponent. It will be that we're serious there, but it's positive. When you change one of the support of the measure of the matrices in the support and change it by the rotation, what it happens again, you have here expanding in the horizontal, contracting in the vertical, then comes the rotation, changes everything, okay? So now you're expanding in the vertical and contracting in the horizontal. And again, you have 0 Lyapunov exponent. But what happened here is that the weights goes to 0 faster than the growth of the matrix. And in that case, you have that even though we are in the Wasserstein topology, they're still together, close enough, okay? So what's going on in the non-compact case that doesn't allow us to prove continuity? If you take a measure, for example, take a matrix in the support of the measure, perturb it just a little bit. When you calculate the iterates of the cocycle, you can multiply by the matrix with norm as big as you want. So actually, that small perturbation becomes as big as you want. And that's why the Lyapunov exponents are not continuous in this case. So that's what I wanted to say.
Any comments or questions?
Okay.
You are in a non-compact setting here.
Yep.
Yeah. So you have a counterexample for continuity.
Mm-hmm.
And you have some condition you may have continuity.
Okay, in this context, no, because as I said, when you perturb just a little bit, when you multiply, it grows as fast as you want. But that problem is because the cocycle here, the random product of matrices, is not bounded. Okay, so what I think right now is that, for example, if you consider a different context, for example, the shift of finite type, and you don't consider this linear cocycle, you consider a more general class, which we call fiber-bonded cocycles, but you ask them for be bounded, I think I will be able to prove continuity. This is actually what I'm working on, but I am positive that if you have this boundness of the cocycle, you will be able, using also the Wasserstein topology, to prove the continuity.
Thank you. Any more questions? No? Let's thank Adriana again.